So the last couple of lectures were pretty theoretical, and we're going over some new terms, derive some formulas, right? So in this lecture, we're going to go in the other direction. We're going to look at some specific problems, see how we can actually do some counting and apply those formulas that we spent those lectures deriving. So pretty straightforward here to start with. How many ways can we arrange the letters of the word Oscar? Okay, what's an arrangement, right? And we're counting them, so this is the kind of thing we've been talking about. When we're talking about words, the order of the letters matters, right? OSCAR is different from SOCAR and so forth, right? So since the order matters, that's going to be a fundamental question we're going to be looking at in every one of the questions we're talking about here. The order here matters, so this is an example of a permutation. Right, so we're going to be thinking in terms of using that permutation formula. So I have 5 things, and I'm looking for 5 permutations, right? Because I'm arranging all of the letters. So what I'm looking for here is 5p5, which our formula says is 5 factorial over 5 minus 5 factorial. That's 5 factorial over 0 factorial. 0 factorial is 1. So this is just 5 factorial. Remember what that factorial means now. This is 5 times 4 times 3 times 2 times 1. You can multiply that out. You can go to scientific calculator. They all have that factorial button on them, so you can have your calculator do the work for you. Either way, this comes out to 120. All right, so how about the second question here? How many ways are there if the first letter has to be R? Right, well, if we use our old multiplication rule method for doing this, we'd think there's 5 letters here. I've got one choice for the first one, because that one has to be R. Then I have 4 letters left for the second spot, 3, and then 2, and then 1 here for the last one. You multiply them all together, you get what 24, right? You do the multiplication. Right, and that's fine. But how can we interpret this as permutation, right? Using our new notation, our new formula. Well, essentially what this is saying here is that I don't have a choice for what goes on in that first spot, right? That's not a choice I get to make. What I do get to choose is I get to take the 4 remaining letters and arrange them in a group of 4. Right? So in other words, if thinking of this as a permutation, this is actually a 4 permutation of a set of 4 elements. So the formula here says 4p4, which is 4 factorial over 4 minus 4 factorial. Just like we saw over on the left side, 4 minus 4 is 0. 0 factorial is 1. So this is just 4 factorial, which, again, if you do have the multiplication or just ask your scientific calculator, that does come out to 24. Right. So this is kind of the second thing I want to point out when we're talking about these questions. First, we want to ask, does the order matter or not? And second, you really want to focus on not only the choices that you have to make, but in this question, the choice that I didn't have to make. Right? At the end of the day, I really only had to make 4 choices here, and that was reflected in the final calculation. So, how many possible 5-card poker hands are there? Well, and anytime we're talking about a deck of cards, we're assuming a couple of things. You're going to assume it's a standard 52 card deck, and you're going to assume that the deck has been properly shuffled. So choosing a card from the top of the deck, bottom, like wherever, is essentially a random choice. All right, so how many possible 5-card hands are there? Well, like I said on the last slide, right, the first thing we have to do is ask, does the order in which I make these selections matter? And here, no, it doesn't. It doesn't matter if you get dealt the 10 of hearts first or the 10 of hearts last. At the end of the day, all that matters is which card's in your hand. So because the order here does not matter, I'm looking at a combination. Right? And what are my numbers? Well, this is a 5 combination because I'm choosing 5 cards to go in my hand, and I'm choosing from a set of 52 cards. And so this is going to be 52, choose 5, which is 52 factorial divided by 5 factorial times 52 minus 5 factorial. Now, you could go to your calculator. Your calculator will handle all of these numbers just fine and give you the final result. But I want to show you something here. This is a little technique. It's not used very much today, I don't think, because calculators today can do just fine with some fairly large factorials. But there are times where this comes in useful, right? So I want you to be aware of this. So here's what I'm going to do. This is 52 factorial over 5 factorial. 52 minus 5, that's 47 factorial. Right, now watch what I'm going to do with the numerator here. This is 52 times 51 times 50 times 49 times 48. And I'm actually going to stop here. Because what happens next? Next is 47, 46, 45, right? All the numbers from 47 on down. So let me write a couple in here. 47 times 46 down to 2 times 1. And this is still all over 5 factorial times 47 factorial. Well, look at this part here. 47, 46, all the way down to 1. This part here is 47 factorial. So that's going to cancel with this 47 factorial in the bottom, and all that's left is 52 times 51 times 50 times 49 times 48. But if you're doing this on a non-scientific calculator, because that's all you've got, available, okay, now you've just really narrowed this down to a much more doable multiplication. We can actually go a little further with this. This is over 5 times 4 times 3 times 2 times 1. That's 5 factorial. 5 times 2, that's 10. That reduces this 50 down to 5. 4 times 3, that's 12. 12 goes into 48 4 times. And we've simplified the multiplication even further, right? If you've got a scientific calculator handy, not something you're really going to have to worry about. But, maybe you don't. And there will be some other times you'll see as we go along here when being able to do this particular kind of simplification is going to help us out. So now, go onto your calculator. We need the final answer, right? That's going to be 2,598,960. So that's the total possible number of 5 poker hands, that you can be dealt from a standard 52 card deck. So we've got another poker example here, right? And so we're talking about another 5-card hand from a 52 card deck. And I want to know, what is the probability of being, it's not the probability, that's a later chapter. I want to know how many different ways can we be dealt the kind of hand that's called 2-pair. Right, and there's a lot of details in here that are just meant to rule out some special cases. 2-pair is a hand where we have 2 cards that have one value, 2 cards that have another value, and a fifth card that has a third different value. All right, so for example, we couldn't have a situation where the 2 pairs have the same value. This is no good. It's actually a different hand. It's called 4 of a kind. We also can't have a situation where that 5th card has the same value as one of the other pairs, because again, that's a different hand. It's called a full house. Okay, so all of those rules in there are really just meant to rule out those special cases. So, how can we make these? How many ways can we make these choices? Well, the first thing I want you to notice is that we are talking about combinations here again, because it doesn't matter if you get the 10s first or the 10s last. Still, in the end of the day, all that matters is what cards are in your hand. So we are going to be using the combination formula here. So what choices are we making? Well, looking at the 2 pairs, I have to choose 2 different ranks, 2 different values, and they have to be different. Right, and I have 13 of them, ace up to 10, plus the jack, queen, and king. I have 13 different ranks to choose from. Okay, so how many different ways can I just choose the ranks of those first two cards. Well, that's going to be 13, choose 2. And now I have to choose the suits for every card, right? And excuse me. There's 4 different suits: diamonds, hearts, spades, and clubs. So looking just at this first pair, I have 4 suits to choose from, and I have to choose 2 of them. And then I'm gonna make a second choice here to get these 2, and I'm splitting these 2 out separately because it's okay to have duplication here. I could have hearts and diamonds for the first pair and hearts and diamonds for the second pair. That's perfectly okay. So to get the suits from the second pair, that's 4, choose 2. Then I have this last card here. Okay, I have to make one choice here, right? Because there's only the one card. And I have, at this point, 11 ranks, 11 values to choose from, because I'm not allowed to duplicate the ones I chose for the first 2. So this will be 11, choose 1. And I have to choose 1 suit from any of the available 4. And that's it. That covers all my choices. So now if you go to the formula, 5 times, right? 5 different combinations here. Multiply all those numbers together. You should end up with a total of 123,552 possible outcomes. So here we've got a manufacturing example. And a manufacturer, he has 10 apps that can be installed on a new device. And due to memory limitations, he can have at most 3 apps on the phone. I want to know how many different possible devices can the manufacturer make. Well, first, I'm seeing combinations in here, right? Because at the end of the day, when you get this phone at the store, wherever you're buying it, you don't care in what order they put the applications on the phone. All you care is which ones are there, right? So we are going to be using the combination formula here, but the problem is I don't know how many choices I have to make. Right? Because the description here says at most 3. Could be 2, could be 1, right? I don't know. So remember from our previous discussion, when we don't know the number of choices we have to make, this is a situation where I'm thinking we're going to bring the addition rule into the process. Right? So what I'm going to do is I'm going to count the number of phones with 3 apps. I'm going to count the number of phones with 2, the number of phones with 1, and it's a little bit of a weird choice, but the description didn't rule it out. So I'm also going to count the number with 0. Then I'm going to apply the addition rule. All of these combinations are distinct. There's no way you can have both 3 and 1, for example. So the addition rule applies here. I'm just going to add these all together. All right, so what are my numbers going to be? I'm choosing from 10. So this first one is going to be 10, choose 3, plus 10, choose 2, plus 10, choose 1, plus 10, choose 0. All right, so now you're going to the formula, and you haven't had a lot of practice with the formula yet, so I'm going to go ahead and write this out so you can see what's happened. This is 10 factorial over 3 factorial times 10 minus 7 factorial plus 10 factorial. They're all going to have 10 factorial in the numerator over 2 factorial times 10 minus 2 factorial. Excuse me. This should be 10 minus 3 is 7. Right? I kind of just jumped the gun and put the 10 minus 3 in there. Plus 10 factorial over 1 factorial times 10 minus 1 factorial plus, and the last one, 10 factorial over 0 factorial times 10 minus 0 factorial. All right, so what do we end up with? All right, and I'm actually going to start down here at this end because it's a little more interesting down here. 0 factorial is 1. 10 minus 0 is 10. So this is 10 factorial divided by 10 factorial, which is 1. Right, I want to stop and think about that for a minute. Hopefully that makes some sense to you. Right? How many different ways can we choose nothing? from a set of 10? Well, there's only one way, right? You don't choose any of the individual parts. All right, so this one, the next one going to the left, this ends up being 10 factorial over 9 factorial. Well, 10 factorial divided by 9 factorial is just 10. And okay, now these last ones here, you're maybe going to want to go to your calculator, but you kind of do these in your head. 10 minus 2, that's 8. So this is 10 factorial over 8 factorial, which ultimately is just 10 times 9. 2 factorial is 2. So this is 90 divided by 2. That's 45. And this last one, this is 10 factorial over 10 minus 3. That's 7 factorial. So that's 10 times 9 times 8 divided by 3 factorial. 3 factorial is 3 times 2 times 1. That's 6. So this is 10 times 9 times 8 divided by 6. 9 times 8 is 72. 72 divided by 6 is 12. 12 times 10 is 120. All right, good. There you go. Add all of these up. 45 and 10 is 55, plus 1 is 56, plus 120 is 176. And there's your answer. Okay, so one thing I want you to really kind of pick up from this question and from the previous question, with the two pair, we've got these new formulas, and that's awesome, and we use them in both cases, but in both of these cases, we still needed the multiplication rule and the addition rule to get to the final result. Okay, so I don't want you to think that these permutation and combination things that we've done have replaced in their entirety the multiplication and the addition rule. They haven't. Right? They've expanded on them, and there are absolutely going to be situations where we need to take all of these things and combine them together to get our final results. All right, so now you've got some idea of how these formulas are used. If you're following along on the website, this is the time you really want to go to the practice area, work on some of the questions there, look at my solutions there, to get some practice with this, because these combinatorics questions, more than anything else we're talking about in all of discrete math, really requires you to start thinking differently than the very algebraic way of thinking you're used to from most students from their prior experience. So you're really going to benefit from jumping in and doing some practice questions, trying to apply these things on your own, then looking at my solutions and comparing. All right, so where are we going next? Well, there's more that we can do with these permutations and combinations. There are some special scenarios that we haven't addressed. For example, what if you're arranging all of these things in a circle? Because then if you take your arrangement, for example, let's say we have A, B, and C. Well, if you take this and you rotate, then you get C, A, B. But if you think about seating people at a table, for example, these are really the same seating arrangements. Everybody is sitting next to the same person they were sitting next to in both scenarios. Right? So do we really want to count these two arrangements as separate? And if not, how can we adjust for that? Right? Another scenario we're going to look is what if you can't tell some of the objects apart? For example, what if we wanted to think about how you can arrange the letters in the word follow? Well, there aren't really 6 different things here, right? If I put little subscripts down here, so just for the moment we can distinguish between these two L's, this arrangement really is the same one as the previous one, right? How can we account for this? All right, these kinds of special cases are what we're going to look at in the next series of lectures.